This video will cover another example of finding eigenvalues and eigenvectors for a 3x3 matrix. For the matrix A here, we want to find the eigenvalues and eigenvectors. So let's start by setting this up as we always do. A minus lambda I is 1 minus lambda, minus 2 minus 1, minus 4, 1 minus lambda, minus 2, 8, 8, 7 minus lambda. So looking at this matrix, there seems to be no really nice, neat way to go about row reduction to make this look nicer, unless you wanted to like swap some columns around, do some weird stuff. So we're just going to go right at this determinant with cofactor expansion along the first row and see what that gets us for this determinant. So determinant of a minus lambda I should be standing along the first row. The first is always negative 1 to the 1 plus 1, which is positive, times 1 minus lambda times the determinant of the opposite matrix. And then we'll see negative 1 to the 1 plus 2, which will be odd, or negative 1. Negative 2, determinant of that bit. Negative 1 to the 1 plus 3. Negative 1, determinant of that minor. And so working all this out, we're going to see the following. 1 minus lambda. 1 minus lambda. 7 minus lambda plus 16. Plus 2. Negative 4, 7 minus lambda. Plus 16, and then minus 1 times negative 32 minus 8, 1 minus lambda. We can then try to expand all this out and see what happens. And yet again, nothing like super convenient, so let's just expand everything out into an entire polynomial and see if we can figure out a root once we get to that polynomial at the end of the problem. So I'm going to expand all this out. This is lambda minus 1 squared, 7 minus lambda, 16 minus 16 lambda, minus 56 plus 8 lambda, plus 64, plus 8 minus 8 lambda. Now expanding out this product here, and then we try to simplify. So I see right now, I see a minus 8 lambda and a plus 8 lambda. Those will cancel, and then we just collect some terms. The negative lambda cubed, I see a 9 lambda squared, minus 14, minus 15, minus 31 lambda, and then a plus 7, that's a minus 40, so minus 33, plus 31, plus 39, and I want to know where this is 0. So again, it's not screaming at me what a root of this would be, but I can check for integer roots by looking at the factors of 39 by something you probably learned way back in like pre-calculus. I can look at 1, 3, or 13 to look for roots that are factors of 39. So I plug in 1, I get negative 1 plus 9 minus 31 plus 39. That's not 0. If I plug in 3, I get a negative 27 plus an 81 minus a 93 plus 39. That's a negative 120 plus 120. That's 0. This means 3 is a root of this polynomial, and so lambda minus 3 is a factor. So to get the rest of the polynomial, we have to divide this by lambda minus 3. I'm going to switch the sign on everything to make it look a little nicer writing this out. But you can leave the minus sign and that'll work out fine as well. So doing good old synthetic division here, right? Figuring out what goes into the highest term as good as possible, plugging it in, simplifying down and canceling. And as expected, 13 lambda minus 39, this has 0 remainder, which it should because it's a factor. And so we get that this is the rest of our equation. So we learned then that determinant of a minus lambda I equals negative lambda minus 3 times lambda squared minus 6 lambda plus 13. So we get an eigenvalue here at lambda equals 3, and this doesn't factor. So quadratic formula is our next resort, which tells us that for the other two roots, we get lambda is 6 plus or minus square root of 36 minus 4 times 13 over 2. 4 times 13 is 52. 36 minus that is negative 16. 6 plus or minus root minus 16 over 2, or 3 plus or minus 2i. We have one real eigenvalue and then a complex pair of eigenvalues at 3 plus or minus 2i. So to fully solve this out, we have to find the eigenvector that corresponds to the real eigenvalue 3, and then only one of the two for the complex pair, because otherwise it will automatically be the complex conjugate. Let's start with the real eigenvalue, lambda equals 3. So I want to subtract 3 along the diagonal of that matrix and see what I get. If I do that, I get the following matrix. And I want to row reduce to hunt for solutions. I can see right off the bat that the first and third columns are just multiples of each other. So if I do something like row 2 is row 2 minus 2 row 1, and row 3 is row 3 plus 4 row 1, I'm going to get minus 2 minus 2 minus 1 in the first row. Then if I do minus 4 plus 4 is 0, minus 2 plus 4 is 2, minus 2 plus 2 is 0, and then 8 minus 8 is 0, 8 minus 8 is 0, 4 minus 4 is 0, which means this becomes minus 2 minus 2 minus 1, 0, 2, 0, 0, 0, 0. I can divide this out to get a 1 here, which then tells me in terms of a system, I have minus 2 v1, minus 2 v2, minus v3 equals 0, and v2 equals 0. So v2 is 0, this term is gone. I'm left then with v3 equals minus 2 v1. In this case, I will pick v1 to be 1, then v3 is minus 2, with v2 being 0 gives me an eigenvector here of 1, 0, minus 2. And then next we can look at the complex eigenvalue, which will take the plus version here, 3 plus 2i. So we want to subtract this from the diagonal of our matrix, which will give us the following, which we can then collect the real and imaginary parts to give us minus 2 minus 2i, minus 2 minus 1, minus 4, minus 2 minus 2i, minus 2, 8, 8, 4 minus 2i. Now to try to do row reduction here, I'm going to first multiply the first row by the complex conjugate of the thing in the first entry. I want there to be no complex numbers in this first column to do row reduction. I'm going to do row 1 times minus 2 plus 2i. And then I'll just write that out. And then do the complex multiplication. So if I do that, this will be a 4 minus 4i plus 4i plus 4 again. So this is just an 8. 4 minus 4i, 2 minus 2i. Now I'm going to divide the first row of the matrix by 2. I know there's more even numbers, but just to make the row reduction look simpler, I'm going to divide the first row only by 2 at this point. 4, 2 minus 2i, 1 minus I, the rest is the same. And I can do row reduction. I can now cancel out that first entry in rows 2 and 3 using the 4 in the first row. So this gives me that I want to do row 2 is row 2 plus row 1. Row 3 is row 3 minus 2 row 1, which gives me the same in the first row. 0, minus 2i plus 2 minus 2i, minus 2 plus 1 minus I, and then 0, 8 minus twice 2 minus 2i, and 4 minus 2i minus 2 times 1 minus I. Simplifying this out, negative 4i, negative 1 minus I, 4 plus 4i, 2. Now we again want to get to redundance in these two equations. So we could use this part here to get to redundance. That wouldn't be a terrible idea. But to stick with the process we've been doing so far, we will use the second column to do it. So you could just multiply the conjugate of this number, and then you have two real numbers here to use to compare the equations. But to simplify things and keep the process the same, we're going to use this column here again. I'm going to multiply row 2 times I and row 3 times 1 minus I, because that's 4 times 1 minus I. And if I do that, first row does not change. 0, negative 4i times I is a positive 4. And this will lead me to a 1 minus I, because I will get a minus I when the I hits the 1. And then I times minus I is plus 1. And then in the third row, I get a 0. I get a 4, 1 plus I, 1 minus I, then 2, 1 minus I. 1 plus I times 1 minus I is 2. So I'll get 1 plus I minus I plus 1. So I will get 2 there, giving me that this is equal to 4, 2 minus 2I, 1 minus I, 0, 4, 1 minus I, 0, 8, 2 minus 2I, and we see a redundance like we wanted. These two rows here are the same up to a scalar multiple, so they will cancel in the row reduction, giving me a final reduced matrix of 4, 2 minus 2I, 1 minus I, 0, 4, 1 minus I, 0, 0, 0, which gives rise to a system of equations to solve as 4v1 plus 2 minus 2I v2 plus 1 minus I v3 equals 0, and 4v2 plus 1 minus I v3 equals 0. So what I'm going to do is I'm going to pick v3. I'm actually going to choose 4 here and not 1. Why am I choosing 4? I'm choosing 4 because that'll make this part work out nicer, because then I know what v2 has to be. So v3 is 4. And this equation here tells me that 4v2 equals I minus 1 times 4, or that v2 is I minus 1. Then we can use these two values of v2 and v3 to solve for v1 using the first equation. The first equation tells us that 4v1 plus 2 minus 2I times v2, which we know is I minus 1, plus 1 minus I times v3, which you know is 4, has to equal 0. We can expand everything out here. This product here becomes a 2I plus 2, because minus 2I times I is negative 2I squared, which is plus 2. And then minus 2 plus 2I. And then plus 4 minus 4I equals 0. I see a 2I, a 2I, and a minus 4I, and a plus 2 and a minus 2. So what I end up with is 4v1 plus 4 equals 0, or v1 equals minus 1. The vector I get here is minus 1, I minus 1, and 4. So to collect our answers, we have lambda 1 is the real eigenvalue of 3, with eigenvector 1, 0, minus 2. We have the first complex eigenvalue 3 plus 2i, the one we actually solve for, which has eigenvector given by negative 1, I minus 1, and 4. And we have our second complex eigenvalue 3 minus 2i, whose eigenvector will be the conjugate of the one for v2, so negative 1, negative I minus 1, and 4, because the conjugate means to make the imaginary parts negative. So there is your set of eigenvalues and eigenvectors for this matrix A. We saw that we had a matrix that had one real eigenvalue and then a pair of complex eigenvalues, and this led us to this method here to find these eigenvalues and eigenvectors for this matrix.